Okay, so we are going to because there's a couple people gone today for knowledgeable, and then I think also for my 6th grade. I don't know, just because.
I love you.
All right, so whoa, easy. So we are continuing our study of circles, okay? And so now we're going to focus in on the arcs and the angles. So the first thing that we did in the chapter was we looked at relationships between tangent lines for the circle. And then yesterday and the day before, we talked about how chords do fun things to circles. And now we are going to look at arcs and angles. So it says many arches that you see in structures are semicircular, but Chinese builders long ago discovered that arches don't have this shape. The Zhaozhou Bridge, shown below, was completed in 605 CE. It is the world's first stone-arched bridge in the shape of a minor arc, predating other minor arches by about 800 years. So whoever figured out how to make that bridge not only made a bridge that has been in, like functional use for almost 3,000 years. So that's pretty cool. But they also beat everybody else on the planet by about 800 years. So that's some smart stuff right there. Okay? All right, maybe there's been some time travel involved. All right, in this lesson you'll discover properties of arcs and the angles associated with them. Okay? So what we're going to do today is we are going to look at inscribed angles. So let's get that going here. What is an inscribed angle? Touches the circle, yeah. Okay, so if I start with the circle like this, and I wanted to make an inscribed angle, then I would need my vertex to be on the circle itself. Okay, all right. So what we're going to do is we're going to compare the measure of the inscribed angle to the measure of the arc itself. And it is not very, let's see, how do I do this? All right, so what we got going here is we got a circle, and we got an arc, and we have an inscribed angle. And what we're trying to do is we're trying to figure out, is there a relationship between the measure of this angle and the measure of the arc? Yes?
Okay, the point to the angle perpendicular.
Oh, so you want to go, say that one more time?
The point to the angle, point of the triangle perpendicular away
From the center of the circle, so this point here and this point here are the same distance from the center. Okay, yep, that is definitely true because those are what? Radii of the circle. Okay, awesome. How do you think the measure of this arc relates to the measure of this angle right here? You think they're the same? You think it's a third? Aaron?
I think it's the same.
Okay, what angle do you know has the same measure as the measure of this arc? Right, when it goes to the center of the circle. So if I make this angle right here, then you know if I measure that angle, that the measure of that angle is going to be what? 88.31 degrees, okay? Does this angle right here look like it's the same measure as this one here? Totally the same.
Yep,
Okay.
exactly the same.
Well, let's measure it and see. Okay, no, totally not. All right. It's about what? It's about half. Okay, so if I take this thing right here and divide it by, if I go, all right, so if I go this divided by that, you're saying I'm going to get a half? Okay, yeah, about. How about exactly? Not about at all. All right, and then once again, with this fun software that I wish we had on those iPads, you can see once again that if I change this, okay, what stays true about the measure of the arc and the measure of the central angle, which I have told you already? They stay the same. What happens to this ratio right here? It also stays the same, okay? And so that is our first conjecture of the day. The measure of an angle inscribed in a circle is what? 1/2 the measure of the arc, okay? So very simple relationship, real nice relationship. Central angle and arc, those are the same. Inscribed angle and arc, the inscribed angle is half of the arc, all right? How do you feel about that?
Really confident.
Really confident, really good, really useful information. You got this? Okay, all right. Okay, what about if I throw another, so this thing right here, oh, decent, all right. Okay, what if I throw another angle in here that goes to the same arc right there, okay? What do you think is true about this new angle that I drew? Let me get rid of this one that's a little confusing. What do you think is true about those two angles that I have there, right there?
They are equal.
How do you know that they have to be equal?
Because it works out like that.
Nope.
Parallel.
What? What happens even if I move this over here? Do you think it's still equal? What, Austin? No, it's not any of that crazy stuff. Oh. What now?
I feel it sounds to me when year just with senior.
What now? Yeah, okay, I see where you're going with that. You could bisect the chords and then do some fun stuff with that. But let me ask you this. We know that the measure of angle CED is 46.09 degrees because it's half of this, right? What is the measure of this angle right here that I don't have labeled?
The same.
It's going to be the same. How come for why?
They have the same arc.
Right, because it intercepts the same arc, right? So if this angle is half of this arc, and this angle is half of that arc, what has to be true about those two angles? They have to be the same because they're both half of the same arc, okay? So, and we see that that is true. So that is our next conjecture, that if you have two inscribed angles that are intercepting the same arc, since this angle right here is half of this arc, and this angle right here is half of this arc, those two angles will be congruent, or the same, okay? So inscribed angles that intercept the same arc are congruent, okay? And that can be a little bit deceptive because it might feel like as I move that point around the circle that is changing the measure of this angle. But you can see from the fact that the measurements are staying the same that it is not, okay? So inscribed angles that intercept the same arc are congruent. All right?
Right.
Okay, I think we have 5 today, so that's fun. All right, now let's apply that to a simple case. It says angles inscribed in a semicircle. How many degrees is a semicircle? 180. Every single one of them, right? 180 degrees, okay? How many degrees will these inscribed angles be?
180
No.
divided by 3.
What?
180 divided by 3.
Wrong and wrong and wrong.
Actually, there were only 2 answers, so you said degree wrong.
How many degrees? Well, 90 degrees, good, because these inscribed angles are always half of the arc that they intersect, right? So if this is an 180 degree arc, then this is going to be 90 degrees. This one right here is also going to be 90 degrees, and that one's going to be 90 degrees. And so what that means is anytime you have a circle and you have a diameter of that circle, I don't know how to make a... Can I construct a diameter? I cannot construct a diameter. Oh, never mind. Let's make the line first. So here's going to be my line. Okay. Oh, that's not in the middle, huh?
I guess not.
No, I can use my fancy. I can use my fancy
circle.
sheeting math tool. There we go. All right, so that means that if I have a diameter of a circle, not a pokeball, a diameter of a circle, if I make a inscribed angle there, this angle will always be what?
90 degrees.
90 degrees, okay, because the measure of this arc right here is 180, and if this is going to be half of that, it doesn't matter where I put that, that's always going to be a 90 degree angle. Okay? It's a swing. So angles inscribed in a semicircle are
So we have to have that one.
right angles. Okay? And that is a direct conclusion from the first thing we did, which was that inscribed angles are half the measure of the intercepted arc. Okay? What's that? Right, we did already know that, but it's not a waste of time because it's something that is worth pointing out. Okay?
Right.
All right? Because it's sort of a special circumstance of that. Okay, what else do we have? Oh, cyclic quadrilaterals. Okay, so first of all, a little bit of a vocabulary word. First of all, a vocabulary word. It says a quadrilateral inscribed in a circle is called a cyclic quadrilateral. Okay? So if you take a circle and you make a quadrilateral inside there, it's going to be a cyclic quadrilateral. Okay? All right, so we're going to make one of those, and then we're going to try to add some of them up. All right, so I have here a cyclic quadrilateral, okay? And I have measured the 4 angles here. Do you notice anything about the sums of any of those angles that stand out to you in particular? Yeah.
Yeah.
Okay, they're going to add up to 360 degrees, but we already knew that because the angles inside of all quadrilaterals will always add up to 360 degrees. Yes?
The opposite ones add up to 180.
Nice. The opposite ones add up to 180. So in other words, if I add angle B and angle D together, because they're opposite each other, these two things are going to add up to 180, right? Laura, you with me? Okay, stay with me. And if I add up angle C and angle A, these opposite ones together, these two angles will also add up to 180 degrees. Okay, so if I go this plus this, then I get 180. And then if I go this plus this, then I also get 180. And again, this is one of those things where I can move the vertices of the quadrilateral around a little bit and change the measures of the individual angles, but the sums will stay the same. Okay? Can anyone explain to me why that's going to be true? Okay, what about a circle makes that be true? Okay, good. A circle is always 360 degrees, right? And we just figured out that the inscribed angles are half of the arcs that they intercept. And so if I take a look at this angle right here, angle DCB, that intercepts, that intercepts this whole arc right here, okay? Then if I look at the angle that's opposite of that, DAB, that intercepts this whole arc right here. What do those arcs always add up to? Because it's a circle, what does Laura say? 360, and half of that will be 180 degrees, okay? So the opposite ones end up cutting out the entire circle, which is 360 degrees. Half of that is 180, so they will always be 180 degrees. All right? So the what angles? Opposite. The opposite angles of a cyclic quadrilateral are supplementary, which is the short way of saying what Manuel was going to say. They add up to 180 degrees. We'll just use the word supplementary. Austin, Nick, Cole, not writing anything of this down?
No, actually.
Oh, okay, good. So Cole's the only one that's just sort of zoning out back there.
Classic.
Okay.
I'm trying to think
Hey,
of
do it.
basketball games tonight, like who's going to play. 'Cause I don't think
Okay, now we are going to investigate the arcs formed by parallel lines, okay? So we talked about already yesterday, if you have a segment that goes through 2 points of a circle, that's called a what?
Chord.
A chord. If you take that segment and turn it into into a line, thank you, thinking ahead, then that is a, bless you, and insight, then you call that a secant. So a chord is technically a segment, and a secant is a line, okay? So now what we're going to do is we're going to take start with a circle again, and we are going to make a couple of parallel lines, all right? So I'm going to start with, I guess, a line. Okay, so there is my line. Now I need to make a line parallel to that. So there is my parallel line. Okay, so now what we're trying to do is we're trying to figure out what's true about this, the measure of this arc right here, and the measure of this arc right here. Yeah, they look like they're probably the same. Okay, and if I was cooler, I don't really quite get how to measure that arc. So you're just going to have to trust me on that. But yeah, since those two lines are always going to be parallel, can you see that the arcs that they intersect are going to be congruent? Okay, does that work for you? You take my word for it kind of deal? All right? Okay, so parallel lines intercept what kind of arcs on a circle? Parallel lines intercept, yeah, to the drawing. So these two parallel lines intercept what's true about these two arcs? They're the same, right. So parallel lines intercept congruent arcs on a circle. Yeah, that's the word that we are looking for. Parallel lines intercept congruent arcs on a circle.
I know,
Do I
right?
have an A in this class? I have an apple.
I don't want anything to do with that
Kind of
apple.
has a face on it.
I don't want your apple, whether it has a face.